Hello everyone, Yicheng here. Today we're going to talk about the power electronic circuit inside an induction cooktop. Let's first start with the structure of this induction cooktop that we're going to show today. So the outermost layer of this induction cooktop is the glass ceramic surface, which serves as a durable heat resistance material for cookware placement. Directly beneath this surface is the induction coil made of copper. When the cooktop is powered on, the power electronic circuit that we're going to talk about shortly will generate a high-frequency alternating current through this coil. This oscillating current will then create a rapidly changing magnetic field above the cooktop's surface, which induces large eddy currents in the base of the vessel. And finally, this circular eddy currents will generate heat in the base of the vessel through resistive heating. Shown here is a simplified schematic drawing of this portable induction cooktop. It is powered by the 120 volt 60 Hz grid voltage represented here as V grid. This AC input voltage is then rectified by a full-wave bridge rectifier composed of 4 diodes to produce a non-negative voltage on the bus capacitor, which is labeled as CB over here. In this application, a stable DC bus voltage is not required. Therefore, the value of CB is typically small in order to reduce the size and cost of the system. Consequently, as we will see later in the scope shot, the bus voltage, labeled as VB here, is a rectified sine wave with some ripple rather than a stiff DC voltage. After that, we have a half-bridge resonant inverter composed of 2 switching devices, one induction coil, which is modeled here as an equivalent inductance LEQ and an equivalent resistance REQ, and 2 resonant capacitors, which has a value of CR over 2, as shown here. This resonant inverter will then generate a high-frequency oscillating current through the induction coil that creates a fast alternating magnetic field, which finally produces the eddy current in the base of the vessel for resistive heating. Now let's take a look at the experimental setup. So here is our experimental setup. We're using a current probe to measure the current flowing through the induction coil, which is shown in the purple waveform here on the scope, and also a differential probe to measure the voltage across the bus capacitor, which is shown as the green waveform here. Now, let me turn on the induction cooker. Okay, so here from the noise, I guess you can already see that the induction cooktop is working very hard to generate heat. Let me turn it off, and now let's take a closer look at the waveform. Here on the screen of the oscilloscope, we have the green waveform showing the bus voltage VB, and the purple waveform showing the current flowing through the induction coil IL. As we can see over here, the bus voltage is a rectifying sine wave at a twice grid frequency, which is around 120 Hz. The coil current IL follows this rectifying sine wave as its envelope, but it's oscillating at a much higher frequency. Now let's zoom in into this smaller period of time so that we can see the details of the coil current IL. As we can see over here, the coil current oscillating at a much higher frequency and at an amplitude around 30 amps. Here, as we can see, the frequency of the inductor current is close to 30 kilohertz. And this high-frequency alternating current will create a rapidly changing magnetic field on the surface of the cooktop, which finally induces the large eddy current that is needed to generate the heat in the base of the vessel. This demonstrates how power electronic circuits can be applied to our household appliances that we see in our daily lives. All right, that's all for today's demo. Thank you and see you next time.